Everything good?
Yeah, please go ahead.
Okay, thank you. Yeah, so thank you very much for the invitation to be here. I do have to say that the TASTES conference last year, brought out the shirt here, I don't know if everybody can see that, was really one of the most fantastic experiences of my physics career. It's really amazing, and I cannot wait to be back in South Africa with all of you, hopefully very soon, next year. But today I will tell you a little bit about what we've been doing really on the ab initio perspective of pushing these types of calculations, not only to the medium and heavy mass region of the nuclear chart, but really applying now our capabilities to answer some of the fundamental questions where in beyond standard model physics where nuclei are relevant. And of course, I think I don't have to introduce too many of these topics, but just very quickly, of course, things like neutrinoless double beta decay, where, of course, this is a hypothesized process where if it is found to exist, this will really at once give us a laundry list of new physics, including, of course, lepton number violation. It will tell us about the character of the neutrino. And in the situation of sort of standard light neutrino exchange through this pretty typical formula here, we could get from some observed half-life to the effective mass of the neutrino, which of course would really set the absolute mass scale of the neutrino, which is one of the most fundamental unknown questions in all of physics. But of course, in order to get from this proposed half-life to this effective neutrino mass, we need this matrix element, which is something that can only be calculated within nuclear structure theory. And we'll sort of take a look at this in a little bit to see how the current status and what we've been able to do over roughly the past year or so. Unfortunately, have not seen too many of you over the past year, and we've made some pretty interesting progress. So the second topic that I'll be discussing kind of along the way here, in terms of course, one of the biggest questions in beyond standard model physics is, what is the nature of dark matter? And we know it's out there. We know, okay, this is doing its own thing, my PowerPoint. We know it's out there, and in some way we hope to learn how it is, in some way what it is. And the most promising, perhaps, a way that we might be able to do this is what we call direct detection, where some dark matter particle, typically some weakly interacting massive particle, a WIMP, will interact with a standard model particle, typically a nucleon within a nucleus, and we're there to see that event take place. But of course, in order to go from that sort of a picture where we have to know how the nucleus itself would react to such an event, we need this object that we call the structure function, which is again very similar to that matrix element in neutrinoless double beta decay, which is something that can only be calculated from nuclear structure theory. And of course, you need this in order to sort of put these typical sort of WIMP nucleon exclusion plots from all of the different experiments taking place worldwide onto one plot like this. So of course the motivation is clearly there, but so now what are we after? So there have been throughout the history of the field many different ways of describing atomic nuclei, but what we're after, especially since in both of these cases the physics that we're after has no there's no experimental data which we can use to sort of inform our theory. There's no observation of neutrinoless double beta decay yet to get that matrix element potentially, or there's no observation of dark matter yet. So if we want to have these theoretical inputs, the idea is that we want to do this from sort of a first principles, a sort of ground up picture. And so that's what we're after. This is what we call ab initio nuclear theory. And in principle, this is extremely straightforward. All we're doing is really, in some sense, solving the Schrodinger equation, which you've all seen in Quantum Mechanics 101. But what makes the nuclear problem particularly difficult is, number one, we don't know exactly what the Hamiltonian is. We can't, there's no rigorous way to connect it to the fundamental theory of strong forces, QCD, at the energy scales that arise in the nucleus. But what we have is a very nice scheme, which I'll only kind of gloss over here, which we call chiral effective field theory. And what this is really a systematic expansion for nuclear forces, which builds in sort of order by order the physics that we're interested in. And you see that by the time we get to kind of subsequent leading orders, that 3 body forces naturally arise. This also gives a consistent way of treating electroweak physics. And in principle, if this is done correctly, which is something that the field is working on, this would allow us to assign rigorous theoretical uncertainties. But even if we know these interactions perfectly, we still then need to solve the Schrodinger equation itself. So we need to solve this in principle, eigenvalue problem of tremendous dimension. And so that's where what we call the, okay, I'm sorry, my PowerPoint is advancing on its own. And so I'm gonna have to be clicking forward and back as we go. But so this is what we call solving the nuclear many-body problem. And so this is, again, a separate area that we're kind of working on in the field, where the idea is what we would like to do is come up with some controlled, systematically improvable ways of solving this equation. And as you can kind of see here, the progress in really the nuclei that we've been able to attack in sort of this first principles perspective is typically grown quite slowly over the years, because typically the methods that had been used, at least from the 90s into the early and mid 2000s, scaled sort of exponentially with increasing mass. But what we've seen is over the past roughly decade that there's been kind of this a set of new many-body methods, which aren't quite as exact as the other ones, but nonetheless are systematically improvable and controlled, and which scale more polynomially. So what we've seen over the years is really an explosion in the reach in ab initio nuclear theory. And again, this plot was one of these I've back in 2016, 17, where if we were to update this today, we can attack way beyond nickel 56 and indeed at least tin 100. And with what I'll show you today, we can maybe even potentially go to the heaviest nuclei that are out there. So stay tuned. But just because we can reach the heaviest nuclei, that doesn't mean that we can hit everything along the way. And so this is sort of, as of a few years ago, sort of the pattern for what these sort of ab initio many-body methods could hit. They typically do very well near doubly magic nuclei, plus or minus 1 or 2. But beyond that, you can do even in some cases, but there's no method that really attacked like the entire region of the nuclear chart. And that's where we kind of came in with what we call the InMedium similarity renormalization group, in particular the valence space formulation of this. And I'm not going to dwell on this at all, because I want to kind of get to the results. But the idea is that you take these interactions from chiral effective field theory, or from wherever, whatever you like, to 3 body forces. And what the InMedium SRG does is you first construct a approximately unitary transformation, which you basically will go to something like a shell model picture, where the first transformation decouples the core energy or any properties of the core, radius, anything like this. And then we undergo a second approximately unitary transformation, which decouples something that looks like a shell model Hamiltonian. But this is unique for every nucleus that we look at, because we also include essentially 3 nucleon forces between all the nucleons within the valence space for a particular nucleus. So then this will essentially spit out an effective Hamiltonian as well as any effective operator that we're after. And so the fact that we get at once both an effective valence space Hamiltonian and operator is really one of the real powers of this, because at that point, once you have any operator coded up, you can essentially put it through this formalism and calculate whatever you want ab initio, essentially with the same reach as the standard shell model. So I'll show you some of the applications that we've undertaken. So again, not really going into the initial work that we did. Roughly, this allows us to pretty much blanket the chart up through roughly n or z equals 50. And again, there was a couple of years ago, kind of a landmark calculation where we attacked tin 100. But like I said, since we can essentially put in any operator, there are a number of different nuclear structure problems that we can attack. Kind of give a laundry list here. Can't really go through all of these because it would take several talks to go through all of the work we've done here. But I just would like to highlight some of the postdocs that are working with me on really developing this. We've really been able to look at the limits of existence, the drip lines, evolution of magic numbers, really moving to heavy nuclei, as we'll see in a minute, coupling to continuum, treating cross-shell things to get to island of inversion, and so on. But what we're even more excited about is, again, the perspective to really, again, with whatever operators we're interested in, really be able to attack some of these beyond standard model physics questions, like neutrinoless double beta decay, WIMP nucleus scattering. And there's plenty of others that I won't have time to talk about today, which we are working very hard on. And you can even apply this to atomic systems. Turns out atoms aren't even that well calculated beyond things like noble gases. So there's a lot of exciting things that we've been working on. But from the nuclear structure side, a couple quick things that I'm going to be focusing on. First of all, can we apply these now that we can really attack all nuclei in principle with these different chiral interactions, to look at the limits of the existence of nuclei? So that is, what are the drip lines? And so what we did several years ago, we sort of undertook this very large scale ab initio study of essentially calculating the energies of all nuclei up through roughly the iron or nickel region. And what we found was, with one particular interaction, so of course you'd want to look at this with different interactions, but one particular interaction, which we had noticed describes ground state energies just remarkably well, really across the chart. And what we found was that when you really look at sort of the residuals, so that's the difference between our calculations and the experimental ground state energies, really across these roughly 700 calculations, you see a picture like this, where when you start to really kind of do the analysis, what you see is there's really an RMS deviation of only 3.3 MeV in the absolute ground state energy. So since we can calculate the energy of the core plus whatever valence nucleus we're interested in, these are really absolute ground state energies. And so again, just to give a perspective, this is at the level of these sort of kind of first level mass formulas like the Bethe-Weizsäcker can achieve something similar. Of course, we're not going to be anywhere near what you can get with DFT, but nonetheless, we wouldn't expect to be getting that level of accuracy, because we know that there is physics missing in our treatment of the forces, as well as the many body methods. So this is really about as well as we would expect to be doing at this point. But again, if these are only absolute energies, and if we're interested in the drip lines, then what we're interested in when we get to the drip line is really separation energies, because we know we've reached a proton or neutron drip line when the proton, one or two proton or one or two neutron separation energies has reached zero. And if we did kind of a further statistical analysis, which I don't have any time to really go into, what we essentially find is that there's roughly a 1 MeV uncertainty, just looking globally at the discrepancy between our calculated and experimental separation energies. And so kind of assigning this 1 MeV uncertainty across all calculations, we're then essentially able to predict for any nucleus along this chain, the probability whether it will be bound or unbound with respect to 1 or 2 proton or 1 or 2 neutron emission. And so here, just showing a few examples, the 3 Cs, carbon, chlorine, and calcium. So we see really going down the 1 neutron, 2 neutron, 1 proton, 2 proton separation energies. And we really see in all cases, like it's remarkably describing experiment. And so the idea here is, if you're describing experiment where it's known and there's no new degrees of freedom arising near the drip line, within these uncertainties, then we should be able to accurately predict the drip lines. And so that's what this bottom panel in each of these plots shows, is the probability that any particular nucleus is bound or unbound. And so we can kind of then throw this onto a global plot where we can assign, again, we can kind of show these probabilities where blue means it's almost certainly bound, kind of the purple is mostly bound. Red is kind of this toss-up region, pink is probably not bound, and white is definitely not bound. And we can really then compare sort of these ab initio, this really global ab initio prediction with experimental data, where kind of on the proton-rich side, you see very nice agreement where the black dots are the confirmed drip line. These open symbols are the last known nucleus to exist. We really agree very well in the proton-rich side of the chart and in the light neutron-rich, and so therefore you would expect this principle to give reliable predictions in the neutron-rich region from oxygen up to calcium, which is of course really kind of one of the flagship motivations of many rare isotope beam facilities, next generation rare isotope beam facilities. So that's one aspect. So we've really gone global on one hand, but now sort of thinking about how we might be able to go heavy, because really the limitation is purely computational. And it comes in two ways. So since we're dealing with a shell model framework, at a certain point, we're going to have very large valence spaces, and we're going to have large dimensions, which we have to diagonalize in the sort of shell model step of this approach. And as well, it's something simple, but at the same time, a very limiting factor is simply storing these three-body matrix elements. So this has been really the bottleneck to moving to converge calculations beyond this TIN 100 region, is simply, can we come up with a clever way of storing three-body matrix elements? And up until last year, the answer was we really couldn't. But this is why I always like to hire people who are way smarter than I am, because my postdoc now, Takayuki Miyagi, who came from Tokyo, came up with a way to store, since we're doing essentially a normal ordering procedure, which I don't want to get too much into that if I had more time. But nonetheless, the point is, in order to capture these three-body forces, we only need some subset of all of these matrix elements. And so what he realized was a way that we could, instead of storing the full set of three-body matrix elements here, which kind of, and this is sort of this truncation, doesn't really matter what in terms of what we can store, where previous the limitation was roughly 16 here, because if you just think of typical storage that you need on a supercomputer, 100 gigabytes is about what you're going to be, it's going to be your limit. So roughly 16 or 18 was the previous limitation on what we could include. But if you only include the three-body matrix elements that are necessary for this normal ordering procedure, you can really extend the range of what you can store by really going from something like this E3 max truncation of 16 or 18 all the way to 28, or you could even think of 30. And so we have implemented this, and if you just simply look at something like TIN 100 or TIN 132, and you look at the sort of the convergence in terms of this E3 max parameter, really right around here, again, 16 or 18 was a previous limitation, but with these increased capabilities, we're really able to go to 28 and really obtain converged calculations for TIN 132 energies, and radii are already pretty well converged by E3 max 18 or so. So that's already pretty nice. Let me skip this, because what we can then do, we can think about, well, TIN 132 looked quite converged. So at least we're able to extend the reach to something like this, but could we even potentially think of, going to, let me skip this, to something heavier, like really, the heaviest doubly magic nucleus that we know, lead 208. And this was something that we have, again, done this year. And really looking at the convergence of the ground state energy of lead 208 in terms of this E3 max parameter. Again, here, 18 was really the previous limitation. So just to get an idea of, this is where pretty much things stood about a year ago. But with this advance by Takayuki Miyagi, we've really been able to take this all the way to this E3 max parameter of 28, and it's clearly extrapolatable beyond, but we're even working on E3 max 30 at this point. So it's quite clear that at this point we're able to get converged calculations for things now in the lead region, which is extremely exciting, because what we can then do is work with our collaborators who are working on machine learning algorithms, which can really then explore the entire parameter space of these different chiral interactions, where once you sort of train it to some data, you can really literally do billions of calculations of lead 208 and really get sort of a heat map for essentially all chiral interactions at a given order for the predictions of both the ground state energy and the neutron spin of lead 208, and of course having a reliable calculation for the neutron spin in lead 208 is really one of the primary, really one of the holy grail type calculations that we're after. And so that it looks like we're at the point where we could potentially do this in this ab initio perspective. So that's quite exciting. But to get to the beyond standard model physics, again, you can sort of see if we're looking at the candidates for neutrinoless double beta decay, they all lie pretty well within the medium to heavy mass region of the chart, where calcium 48 is the lightest, and things like germanium 76, which is one of the key isotopes in experimental searches worldwide, are definitely within range of this approach, where these guys, again, these heavier ones like xenon were a bit outside our reach. And so just to show, this is sort of where things stood, where this is kind of the typical picture, where with all of these different phenomenological models, there's quite a spread in the prediction for this nuclear matrix element. Yeah, and of course, before we really want to attack double beta decay, we want to make sure we're first describing single beta decay, and this is a picture that we've shown many times, because really looking at this kind of problem of GA quenching over, which is where really theory didn't agree with experiment just at that fundamental level. But when we put in all the physics that we know has to be there, we kind of go from this orange picture or this orange line to this green line, where if we're looking at either the SD shell or the PF shell nuclei, in both cases, when we include the physics of sort of this renormalization of the Gamow-Teller operator, as well as including the effects of chiral two-body currents, then we're really, for the most part, reproducing experiments. Not exactly there here, but okay, up to like the 95 or so % level, we're getting quenching. So we would at least then trust at some level that predictions for double beta decay would be not unreasonable. So let me skip the two neutrino stuff. And first, first we wanted to make sure that we, before moving to the heavier things, that we could benchmark with really exact methods like no coarse shell model in the light nuclei. And that's pretty much what we show here for a series of sort of really fictitious double beta decays from helium-6 to beryllium-6 all the way up to sort of oxygen-22 to neon-22, which is the analog of calcium-48 to titanium-48 from the SD to the PF shell. Regardless of which sort of ab initio method you use, as long as you start from the same set of 2 and 3 nucleon forces, things look to agree pretty well. So again, we want to make sure we're doing as well as we can in any system that we can benchmark before going to these important cases like germanium 76. And so, yeah, here we go. So now that we trust this, we can then take these calculations and apply them, first of all, in calcium-48, which, while it's not necessarily experimentally relevant, it is a doubly magic nucleus. And so that means that a lot of different ab initio methods can really calculate here. So that means that it's ideal for benchmarking our approach versus other ones. And so what we find is essentially here, the top figure is really the convergence in terms of the single particle basis. So this is really sort of the size of your harmonic oscillator basis. So yeah, Emax. So this is 12 would be 13 major oscillator shells and so forth. And here we also show the convergence in terms of this E3 max parameters. This is the storage of 3-body matrix element. So here it's not a problem. We're clearly converged by the time we're E3 max 14 or 16, and things are not a problem. And so our prediction comes in right here. This blue line here, fairly low, lower than most of the other calculations. But as we'll see in a minute, it's quite consistent with other ab initio methods. So this is, but there's, as you saw, there's really no limitation for us to then go beyond calcium-48 because we can easily go up to tin-100 or so. So germanium-76 and selenium-82 are definitely within reach. And so here's our prediction for that nuclear matrix element, which is pretty well below most of the existing predictions. Again, you have to go out to a fairly large E3 max, maybe 18 or 20 by the time you can really reach true convergence here. And a similar picture for selenium-82. So one thing you might have noticed as we go through here that most of these predictions were at the low end, if not lower than all other predictions for this nuclear matrix element. But again, something we want to keep in mind is this is only with one interaction. And so what we want to do is somehow capture any uncertainty that we would have from the nuclear forces and see what we could, if we can maybe represent that here. And so what we did over quite recently, in fact, this plots just came out a couple of weeks ago, as one of my new graduate students really used 5 different kind of the leading state-of-the-art chiral interactions that are out there on the market and perform these same calculations for calcium-48, germanium-76, and selenium-82, which gives us these sort of green bands that I've plotted here. And so what we first of all see is that in calcium-48, there is another InMedium SRG approach, which Heiko Hergert has been developing at Michigan State, and with coupled cluster theory, which of course the standard coupled cluster guys at Oak Ridge, all of the calculations are completely consistent with each other within any uncertainties that we have, starting from the same set of 2 and 3 nucleon forces. So this is exactly what you would hope to see from an ab initio picture. So there's still a lot that would need to be quantified here. But nonetheless, that's the fact that all these different ab initio methods are agreeing with each other is quite promising. And again, you see, there's nothing to compare with yet in germanium and selenium, but we would expect that once they can reach that level, then they would have some agreement. But again, like I said, we can now really extend with this increased E3 max capability, really to go to something like this. And so that means that these heavy guys, which are quite experimentally relevant, especially xenon-136 and even tellurium-130, which is something that's being pursued here in Canada for neutrinoless double beta decay, are within reach. And these really were, again, plots that just came in a week or 2 ago. We're really just, we need to follow the blue in both of these. And really the difference between the dotted and the dashed is really increasing the size of our single particle basis. And we see it's very well converged in terms of that cut, as well as this increasing 3-body forces. And so what we really look to have is now for the first time, really, again, converged almost there. Maybe we need to go out to E3 max 26, but that's not a problem. Converged calculations of the nuclear matrix element in xenon and tellurium. So again, quite exciting. And we're really now working on including all of these other interactions in this type of a picture to hopefully give a band for these guys. But something that, again, these are all coming out on the very low end of the set of matrix elements, which is not good if you're doing the experiments. But again, there's a lot of physics that we still haven't put in yet, so these are nowhere near final matrix elements, and especially there's this big question of the effects of 2-body currents. Yeah, and here actually, some of the things that we're working on next. One of the big effects is not just the 2-body currents, but within the past couple of years, it's really been discovered that there's a leading order contact if you're pursuing this chiral effective field theory picture, there's just kind of this leading order contact interaction which has undetermined parameters, and of course you're talking about neutrinoless double beta decay, there's no data to fit to, and so this is really now maybe the biggest obstacle to being able to claim something close to a final matrix element in terms of this sort of ab initio picture where we have the forces really derived consistently, and then in some ab initio many-body method. So that's where we stand there. What's my time?
I think your time is over, but
okay, that's I didn't see this. I didn't get the 5 minute, but okay. Again, just I'll take like literally 30 seconds here. You can do this essentially the same picture for dark matter, where you're after these structure functions, and it's really kind of the same picture. Where several years ago, well, 2013, you have these nice pictures, including the effects of two-body currents in calculating these structure functions. But both the wave functions and the interactions that are used here to calculate all these nuclei are a phenomenological perspective. But what we've done recently is really then take, again, since we have these operators which we can include in our methods, really calculate the structure functions as far up as we can go, which so far has been, okay, we have good spectra too, has basically been the germanium here. And so, yeah, that's kind of where we stand there. And again, just a lot of other nice, exciting things that we've been doing, but just to give some sense of really the reach and the recent progress in ab initio theory, in particular for describing things like beyond standard model physics. So I will stop there, but I pretty much highlight anybody in blue. This is really all due to fantastic postdocs, fantastic students who I'm just lucky enough to get to show their results. So thank you.
Thank you very much, Jason, for this beautiful talk and impressive and showing us these impressive results on ab initio theory. So now the floor is open for questions. I have one from Jacek in the, I don't know, maybe Jacek wants to
Sure.
ask directly, or maybe I can read the chat. I mean, so Jacek, are you there or?
Yes, yes, I can ask a question myself. So
okay.
I'm interested in the propagated errors of your double beta decay matrix elements, but when you would take into account the fact that your parameters of the chiral interaction also have uncertainties, so your result does not only have an uncertainty related to the basis and the calculation method, but also the inherent uncertainties related to the unknown or parameters of the chiral force.
True. Yeah, so that's that. Yeah, of course, that's yeah, that kind of goes hand in hand with this undetermined coupling is really how you can control the errors from the chiral forces. And yeah, of course, at this point, what we would love from the people who develop the forces are sort of an order by order expansion, or like really order by order forces that we have where there's some uncertainty at each order, which ideally would have some error bar which shrinks as you go to subsequent orders, but we don't quite have that yet. So that's, I think at this point, the best we can do is something like I showed here. We're really taking a wide set of really kind of the state of the art chiral interactions that are on the market. And in each of these, they're done significantly, sort of derived significantly differently, that with different regulators at different orders, some including explicit deltas, some not, things like this, that again, this is not a true uncertainty for this, but you would at least guess that this spread would be somewhat reliable at this level. But that's, again, there's nothing we can do until these sorts of systematic forces are derived. But that's, of course, a tricky perspective. But still, nonetheless, you would guess that this band is at least fairly meaningful.
Thank you, Justin.
But yeah, that's clearly something we have to deal with in the field.
Okay, I think we have time for a quick question or a couple of questions more. So I have one of my own. So I have
Sure.
many, but
Sure, sure.
Which interaction are you using for most of these calculations?
Yeah, so in some sense, yeah. If I had more time, I'd kind of describe a little bit more about the kind of present status of these different interactions. So if we're interested in things like energies, we know that there's this one particular interaction which we've just observed, and so this, you can say this is some sort of a parameter of choice. We've observed describes ground state energies incredibly well. So if we're looking at anything like energies, we're typically going to use that. But there are also a few others that are very recently developed, like this delta Go, which was developed by the Oak Ridge group and Chalmers group, which includes explicit deltas, and it again looks to do fairly well on ground state energies. And similarly with these N3LO, again, these names don't mean anything unless you're in the field, but this is developed by Peter Navratil here at Triumph, which also does pretty well on ground state energies. So if we're looking at energies, we would typically use one of these three, because we know that they'll probably give something reasonable. But again, that's not that uncertainty that you're looking for. Whereas some other interactions will do better for radii, and so you would, again, probably use one of these. But we still always try to give at least some reasonable, use at least more than one typically, to get some idea for the spread of uncertainty that would come from these interactions. But then when you get to double beta decay, you have no idea what it is, so you should really use as much as you can to get some idea for what, and this is probably like a worst case spread would be. But yeah, because again, you can kind of even go back to single beta decay and find out which one did the best in reproducing sort of the sort of quenching pictures. But really, when it comes to double beta decay, everything's off.
The three body is dealt with within the normal order approximation, or
yes, yeah. So the three body force is always normal ordered. So this is, again, if for the students out there, this won't make any sense, but you basically will, you'll take, so the typical normal ordering is you will take into account the three body forces between the nucleons in the core, or like one or two above. But since we're dealing in a valence space, and we have this picture, and you can have any number of nucleons in that valence space, we also take into account, again, with this normal ordering thing, those three body forces. But again, that's an approximation which we always want to check, and typically it's the neglected forces. The neglected effects are fairly small.
Great. One quick question from Alfredo.
Sure.
Hi, Jason.
Alfredo.
Thanks for the talk.
Good. Thank you.
Just one question. When you have these bands of neutrinoless double decay matrix elements, you relate it to the interaction, and this is for me completely opaque physics-wise. I mean, what I mean is when you reduce or increase the matrix element with respect to some reference, what are you changing in the physics of calcium 48 and titanium 48, for instance?
Okay, that we could easily look at, which I don't have any figures here. I mean, there you can look at.
No, but I can tell you one thing. You have a limit in which the matrix element is 0. Huh? You can get 0 if you get the titanium deformed enough. Huh? And if you make the titanium not deform at all, then this will go up to a factor of 2 or 3. So there is a relation, obviously, with the physics, which is more telling.
Okay.
You could look to that, probably.
Yeah. I mean, so yeah.
You know what I mean? It's just on top of that, to know which is your calcium or your titanium in each case with each interaction to select. And one thing just to finish is that this selenium 82 number It is mysterious for me. All the calculation give the same number independently. Selenium and germanium in all the calculation have more or less the same, and in
Typically the
this
same.
thing
Yeah.
they barely touch.
Yeah. Actually, let me go back. I think here they're pretty close. I mean, they're within.
Yeah. This I like. I'm happy
Yeah.
with that. Then when
Yeah.
you go down, really down. As a matter of fact, this error bar is does not include the other number. The blue line is not touching that. If you go to your blue line.
Oh, here. Oh,
yeah.
That's totally.
Yeah, this is selenium, and this is completely. They don't touch.
Oh. Okay. Yeah. Actually, if you look here, this number is a lot smaller. Yeah. This is actually my fault. I didn't update this blue line from a previous talk. But yeah, this should be a roughly 1.23 here, and this is obviously.
Yeah, but this is extremely. Yeah. That's something that you probably need to go to the
yeah.
To the structure.
Actually, if you look
because it's very
here,
strange. This very small number for selenium is. No. I don't feel comfortable with it.
Yeah, actually, neither. Yeah. You can kind of see. Yeah. Okay. So. Right, you can kind of see what happens here. There's this very large uncertainty in choosing the normal. Okay, I don't know. Okay, I guess we understand each other in choosing the normal ordering reference, whether it's the parent or the daughter. And yeah, okay, now I remember what's going on. This is actually something that we need to look at further because it came up in the tin region. It's a little complicated because what can happen is the way we have the code set up is you can either take sort of a naive filling for the sort of the normal ordering, or you can look at the Hartree-Fock spectrum and use that. And so in some cases, there's a big difference between the Hartree-Fock spectrum and the sort of naive filling. And so that's actually what's giving rise to this difference here. And so that actually would be something that we should look at because that could extend the kind of the uncertainties of these
Thank you,
quite
Jason.
a bit.
I understand, but
that's actually a good point.
To mention that to you.
Thank you very much. I think, well, I'm a terrible chairman because I'm really, but
thank you. So
we have time to thank Jason again, and I'm going to thank on behalf of everyone.
Thank you.
So we have to quickly move on to Makito's